Okay, we started off this chapter talking about physical changes versus chemical changes, right? And basically, we've looked at two examples of physical changes so far: temperature changes and phase changes. This is a chemistry class, right? So we got to talk about some chemical changes, and that's what we want to discuss today. Specifically, we want to discuss chemical reactions, right? Chemical reactions. So let's write down a basic chemical equation. All right, make sure that you understand the various pieces, the various parts of a chemical equation. All right, and this chemical equation is going to be the burning of coal, right? Which is an important process. We get about a third of our electricity in the U.S. from the burning of coal. So the coal is predominantly comprised of carbon. So this would be the basic chemical reaction for that process. You have solid carbon. The C tells you which element we're talking about, right? The letter in parentheses here tells you the phase of that compound. So in this case, it's in the solid phase. So it's carbon plus O2. That should make sense because when you burn something, you got to have oxygen in order to burn it, right? The oxygen is in its gas phase, and then that produces carbon dioxide, CO2, also in its gas phase. All right, so we refer to this side of the chemical equation as the reactants. These are the substances that react together, right, to produce whatever's on the right side of the chemical equation. So since this is what's produced, we call this side the products, right? And of course, you may have more than one, right? Often you do. But in this simple one here, we've got two reactants, we've got one product on this side. And like I said, these are the phases, the letters that are in parentheses here. For the phases, the phase symbols are basically G for gas, right? L for liquid. You also have something called aqueous. And aqueous basically means that it's been dissolved in water. So sometimes you'll have something that's been dissolved in water in your reaction. And then finally you have the solid phase, right? So those are denoted by the letters that are inside the parentheses, okay? And so remember why we said that chemical reactions happen. We said this earlier. The whole reason we started studying valence electrons is because these chemical reactions happen because the atoms in there are trying to get a better electron configuration. That's why we said when you look at the periodic table, if the elements that are in the same column of the periodic table are going to have very similar chemistry. Why? Because they have the same number of valence electrons, right? So if I'm in column 2 on the left-hand side, I've only got 2 valence electrons, but I want 8, so I'm trying to get 6 more from somewhere, right? If I'm in column 7 on the right-hand side, I've got 7, I just need 1 more, so I'm trying to get that 1 extra electron from somewhere. So that's why these chemical reactions happen, right? And so let's just look at an example of that as we consider this equation right here. So let me write that down. I'm just going to write it down over here so we can refer to it. Carbon in solid state plus O2 in gas state produces CO2 in a gas state, right? And let's draw the Lewis structures out for those compounds, right? Since we know how to do that. So C has 4 valence electrons, right? It's in column 4A plus O2. We know how to draw the Lewis structure for that. Homonuclear diatomic, 2 oxygen molecules bound together, and then that produces CO2, and CO2 looks like this, right? So you should be able to do that as well. That was last chapter. We learned that. And so notice on this side, carbon only has 4 valence electrons. It's trying to get 8. So this reaction happens here, and so what we have on the other side is everybody's satisfied as far as the valence electrons that they have, right? C has 8 valence electrons now, so it's got that ideal electron configuration and is happy. Let's look at another common chemical reaction, and that is the burning of methane, which is natural gas, right? Many of us, our houses are heated by the burning of natural gas. And so that chemical reaction looks like this. CH4 in gas form plus O2 in gas form is going to yield CO2 in gas form combined with water, which is also in gas form. And this is what we refer to as a typical combustion reaction. It'll be some substance combined together with oxygen. Again, you need oxygen in order to burn it, right? So if it's a combustion reaction, it's going to be combined with oxygen. And the typical products, that which is produced from these reactions, is typically, these reactions are typically carbon dioxide and then water, both in gas form, okay? So we're going to study combustion reactions in detail later on in the year. But let's draw the Lewis structure for this. And so the Lewis structure for these compounds is going to look something like this. Right? Plus the O is going to look like this, right? And so then over here on this side, we're going to have CO2. Was it very much kind of sloppy of me? Whoops. That still doesn't look good. There we go. Plus H2O. Right? So this accurately represents what we have up here in our chemical equation. But if we draw the Lewis structure out, we see that we actually have a problem with this chemical equation. Namely, on this side of the chemical equation, we've got how many H's? 1, 2, 3, 4. Right? Well, on this side of the chemical equation, we've lost 2 H's apparently because we've only got 2 on that side. We have the reverse problem with the O's. On this side, we've only got 2 O's. On this side, 1, 2, 3, we've got 3 O's, right? So if matter can't be created or destroyed, this stuff can't just disappear. And so what you started with is what you're going to have to end up with on the other side. And so how could we make sure, how would this actually happen, right? So that you've got the same number of atoms on one side of the equation that you have on the other side. And the way it would happen is actually that the methane would not react with a single oxygen molecule. It would actually react with 2, right? So if we draw 2 oxygen molecules here, 2 oxygen homonuclear diatomics, right? So for a total of O's, now we've got the same number of O's. Actually, we don't yet, right? So let me finish this. So we're gonna put 2 oxygen molecules on this side instead of just 1, a total of 2, and we're gonna put 2 water molecules on this side instead of just 1. So let's see what happens if we count them up now. Well, we've got 4 H's over here. Guess what? 1, 2, 3, 4. We've got 4 H's over there, right? On this side, 1 C. On this side, 1 C. On the reactant side, we've got 1, 2, 3, 4 O's, and on the product side, we have 1, 2, 3, 4 O's. Right. So now we're balanced. We have the same number of atoms on the left side that we have on the right side. And so if we were to adjust our chemical equation to accommodate this change, then we would actually write it like this. It's actually CH4 plus 2 O2 molecules in gas form, and that produces CO2 plus 2 H2O molecules in gas form. Okay? So now this is what we would call a balanced chemical equation. Right? Because we have the same number of atoms on the left side, on the reactant side, as we have on the product side. Remember, Dalton's atomic theory said that atoms can't be destroyed, right? And even though we know now what he didn't know, that these atoms were comprised of subatomic particles, so it actually could be busted up into these subatomic particles. Still, when it comes to chemical reactions, that statement's true. However many atoms you have on the left side, you got to end up with the same number of atoms on the right-hand side. Okay? So let's count the atoms. Let me show you how you would do that, so you could verify whether or not the chemical equation was in fact balanced. We just sort of went through it, but you shouldn't have to draw out the Lewis structure to do that. You should just be able to look at the equation and count the atoms that way. So let's let's start with one that's a little simpler to explain, and namely 202. All right, if we've got 202 on this side, what you do is you take the big number in the front and you multiply that times the little number, which is the subscript on the element, to determine how many total atoms of atoms there are for that particular substance, right? So 2 oxygen atoms times 2, so 2 times 2, and what I'm going to do to kind of eliminate the confusion here, because when you write down this O, in fact, let me do that here. When you write down an O next to a number, it kind of, you may think that's a 0 instead of an O. So 2 times 2 O's is going to give us a total of 4 O's, right? And so let's count up the number of C's that we have in CH4. So CH4 here, let's take a look at that. CH4. Regarding the C's, we have an understood 1 in front of this C right here. So 1 times the total number of C's in this compound is 1, right? We also have a 1 understood 1 here for the subscript. So 1 times 1 C's is going to give us a total of 1 C, right? And then also in the CH4 we have some H's. So how many H's do we have? You take the big number in the front, which is an understood 1. So 1 times the subscript on that particular element, which is 4 for the H's. So times 4 H's, and that's going to give us a total of 4 H's, right? All right. So now let's move over here to this side. We'll start with CO2. CO2. And for CO2, we've got 1 times 1 carbon atom times 1 carbon atom, because the 1 in the front and an understood 1 here. So 1 times 1 C, that's going to equal 1 C, right? And CO2, we also have an understood 1 in the front here, 1 times 2 oxygen atoms. So 2O equals 2 O's. All right, and now let's look at 2H2O. For 2H2O, we have 2 H's, the 2 in the front times 2 H's here, the little 2, the subscript of the H, so that's going to give us a total of 4 H's, right? And then in this we have a 2 in the front times an understood 1 here for oxygen. So 2 times 1 is going to equal a total of 2 O's, right? And so now that we've kind of written it like that, if we count all of these up here to see if we have the same on each side, this side has 4 O's, right? On this side, we have 2 O's in this compound plus 2 O's in this compound, so we've got a total of 4 O's there. As far as carbon goes, we've got 1 C. Sure enough, we've got 1 C on the reactant side as well, and then we've got 4 H's, and we've got 4 H's on this side as well. So we know then by counting up the atoms that this is in fact a balanced chemical equation. And that's exactly what our next example in the book is going to have us do. Okay, so if you'll look in your book, on page 175, example 1.2, they give us the following equation. It says C6H12O6 in solid form plus 5O2, 5 oxygen molecules in gas form, produces 6 CO2 in gas form plus 6 H2O in liquid form. All right, so that's the chemical equation, and we have to determine whether or not this chemical equation is balanced. All right, so we're going to start with this side of the equation. On this side here, instead of doing it like we did it last time, where we look at each where we look at each compound separately, we're gonna look at the actual atoms and count the atoms up. Okay, so let's start with C. So on this side here, we basically have C, H, and O, right? We have an O here as well. So we're going to do the C's, we're going to do the H's, and we're going to do the O's so that we can see what we have. So as far as C's go, right here I've got 1 times 6, right? The little 6 there. Don't have any other C's on this side of the equation, so we have a total of 6 Now again, I'll use the red so that we will eliminate any confusion there. 6 C's, right? On this side, as far as H's go, we've got an understood 1 in the front here. 1 times, the only H is in this compound, so we look at the subscript here, 12 H's. So 1 times 12 is going to equal 12 H's, right? And then finally, when we count the O's, we've got O's in this compound, and we've also got O's in this compound. So we're going to have to add those together. So there's an understood 1 in the front here. Again, 1 times the little 6 next to the O, right? We'll put that in parentheses, plus 5 times 2 O's here. 5 times 2, right? And so that's going to give us 1 times 6 is 6, right? 5 times 2 is 10. So that's going to give us a total of 16 O's on the left side. All right? Does that make sense? Ha! You can't ask me. Well, you can ask me by email, right? Email me if it doesn't. So what about the C's on this side? Let's do C's first on this side here. We've got 6 times 1 C there, right? For a total of 6. That's the only compound that has a C in it. So we have a total of 6 C's. Looking good so far. That's what we have on this side, right? What about the H's? We'll do H's next, since that's what we did next here. No H's in this compound, so we only have to look at this one. We have 6, the big number in the front, times 2, the little number next to the H, times 2 equals 12 H's. Oh, I'm feeling pretty good, right? We've got 12 H's over here. Let's count up our O's and we'll be done. O, we've got 6, the big number in the front, times 2 O's here, right? But then we've also got to take our O's into account in this one. So 6 times 2 in the first compound. This one here, we have 6 times understood 1 next to that O, 6 times 1. So this is going to be 12 plus 6 for a total of 18 O's. Uh-oh, right? We had 16 O's over here. We had 18 O's on this side. So is this a balanced chemical equation? No, it is not, right? Because we don't have the same number of atoms on the reactant side as we have on the product side. And you can see here how it could work out for every atom in here except for 1. All it takes is 1 to mess this up. And so this one is not balanced. And so what we're going to learn next, what we're going to do in the next lecture, which is next week, is that we're going to learn how to balance a chemical equation. If I give you one that's unbalanced, you'll know how to fix that yourself. All right? So until then, do your homework and let me know if you have any questions. Have a good week.